because a black hole has only a few internal parameters. Most of the information about the matter that went into forming the black hole is lost regardless of the type of matter which goes into a black hole. It appears that only information concerning the total mass, charge, and angular momentum are conserved. As long as black holes were thought to persist forever, this information loss is not that problematic, as the information can be thought of as existing inside the black hole, inaccessible from the outside, but represented on the event horizon in accordance with the holographic principle. However, black holes slowly evaporate by emitting Hawking radiation. This radiation does not appear to carry any additional information about the matter that formed the black hole, meaning that this information appears to be gone forever. The question whether information is truly lost in black holes, the black hole information paradox, has divided the theoretical physics community. In quantum mechanics, loss of information corresponds to the violation of a property called unitarity, and it has been argued that loss of unitarity would also imply violation of conservation of energy, though this has also been disputed. Over recent years, evidence has been building that indeed information and unitarity are preserved in a full quantum gravitational treatment of the problem. One attempt to resolve the black hole information paradox is known as black hole complementarity. In 2012, the firewall paradox was introduced with the goal of demonstrating that black hole complementarity fails to solve the information paradox. According to quantum field theory in curved spacetime, a single emission of Hawking radiation involves two mutually entangled particles. The outgoing particle escapes and is emitted as a quantum of Hawking radiation. The infalling particle is swallowed by the black hole. Assume a black hole formed a finite time in the past and will fully evaporate away in some finite time in the future. Then, it will emit only a finite amount of information encoded within its Hawking radiation. According to research by physicists like Don Page and Leonard Susskind, there will eventually be a time by which an outgoing particle must be entangled with all the Hawking radiation the black hole has previously emitted. This seemingly creates a paradox. A principle called monogamy of entanglement requires that, like any quantum system, the outgoing particle cannot be fully entangled with two other systems at the same time. Yet here the outgoing particle appears to be entangled both with the infalling particle and independently with past Hawking radiation. In order to resolve this contradiction, physicists may eventually be forced to give up one of three time-tested principles: Einstein's equivalence principle, unitarity, or local quantum field theory. One possible solution, which violates the equivalence principle, is that a firewall destroys incoming particles at the event horizon. In general, which, if any, of these assumptions should be abandoned remains a topic of debate.